Welcome to the review of Unit 3. So Unit 3 covered the periodic table. One of the key concepts was Mendeleev, his original periodic table, and he classified that according to increasing atomic mass. That's different than the modern periodic table. The modern periodic table organizes elements by increasing atomic number, which we know now is number of protons. So hydrogen has 1 proton, helium has 2, lithium has 3. Mendeleev's original periodic table was slightly different in that it arranged them by mass instead of number of protons. Elements are arranged in a way that have similar properties within a vertical column, those are the groups, while elements in a horizontal row have different properties. So groups are the ones that go up and down, similar to what you would know as columns. And groups are very similar to each other because they have the same number of valence electrons. So group 1, they all have 1 valence electron. Group 2, they all have 2 valence electrons. Group 13, we know it as 3A. So group 3, they all have 3 valence electrons. Group 4, they all have 4 valence electrons. 5 has 5, 6 has 6, 7 has 7, and 8 has 8. Periods, they don't share similar properties. They're actually very different from each other, and that's where they come up with the idea of the periodic law, or the idea that as you move across the periodic table, you see these trends. So hydrogen is different from helium, but then you get back down here and lithium and hydrogen are similar to each other. Then beryllium's very different, same with boron, carbon, nitrogen, oxygen, fluorine. They're all so different in the period. Then you get down to sodium, and sodium behaves a lot like lithium. And again, that's due to the number of valence electrons. Important classes within the periodic table are metals, nonmetals, metalloids, and noble gases. So these are your metals over here. You have your alkali metals, group 1, alkaline earth metals, group 2, transition metals, and then your inner transition metals right here. Those are your lanthanides and your actinides. You have your metalloids, they're highlighted and boxed in purple, and then your nonmetals, and then the last group, that's your noble gases. Atomic size generally increases across a row and down a column. So basically, as you move to the left, you get bigger. As you move down, you get bigger. So I kind of just drew this arrow. And I think in class I mentioned if you are closer to francium, francium's right here, you are bigger in size. Think of like a big bodyguard named Frank, who's big and tough. He's huge. So cesium would be rather large. Barium would be rather large. Helium would be super, super tiny. Same thing, fluorine would be pretty tiny. Ionization energy and electronegativity are exactly the opposite of that. They decrease from top to bottom within a group and increase from left to right. So helium and fluorine and these elements up here would have a very high ionization energy and a very high electronegativity. Francium would have a very low ionization energy and a very low electronegativity, and anyone near francium. So as you move this way, you get less electronegative and you have a lower ionization energy. As you move down, same thing, you get lower. So the highest ionization energy is up here, highest electronegativity is up here, lowest is down here. Cations are smaller than their parent atoms, and anions are larger. So cations will get smaller. One of the reasons for that, so cations lose electrons to become positive. Remember, electrons are negative. So when you lose negative, it's like a double negative in math class, you get positive. So when they lose those electrons, they actually lose an entire outer shell. So you can see here, this is sodium, and then this is sodium ion. Sodium ion has lost an electron. You can actually physically see it gets smaller. So cations get smaller, anions get larger. So when you gain electrons, you actually get bigger. You can kind of think of it like gaining weight. You get bigger, so gaining electrons, you get bigger. So anions are larger than their atom counterpart.